Thank you, Ben. Welcome to the AASHTOWare Payment ME Design Fiscal Year 26 webinar number 2 on resilient modulus characterization for AASHTOWare PMED. My name is Hari Nair. I am the chair of the Payment ME Task Force, and I will be your moderator for today's presentation. Today's presenter will be Dr. Sri Rao of Applied Research Associates. This presentation is being recorded and will be available on the ME Design Resource website as shown in the screen. Again, I am the chair of the Payment ME Task Force, and Ian Risch of the Georgia DOT is the vice chair. The other members of the task force are Ryan Fragapane, he is the AASHTOWare product director, Ben Said, AASHTOWare associate product manager, Nusrat Morshed with the New Jersey DOT, Kumar Dave with the Indiana DOT, Dulce Feldman with California DOT, Jason Simmons, Utah DOT, Robert Studler with the Maryland DOT, and Diana Podboroshinsky with the Canada TAC license, and Tom Yu, Federal Highway license. A couple of housekeeping items. We encourage you to ask questions, and those will be addressed at the end of today's webinar. If you have questions, please click on the question and answer button to send your question to the host and panelist, and we will address these after the presentation as time permits. Any questions not answered will be responded separately. And now Sri will begin the presentation.
Okay, I think I'm going to go ahead and get started. Good afternoon, everyone in the East Coast, and good morning if you're still on the western part of the US. My name is Sri Rao. I'm with Applied Research Associates, and I'm going to talk today about many different aspects of resilient modulus as it pertains to pavement ME design. It would be nice if you have some experience with the payment ME design, whether it is the desktop or web versions, but overall, you should still be able to follow the presentation if you do not have significant amount of experience with these versions of payment ME design. I'm going to quickly go over some learning outcomes of what we want to achieve today, and then also then get directly into the presentation. And what we wanted to talk about a little bit today is resilient modulus testing and how it's used in payment ME design. Distinguish between resilient modulus usage in AASHTO 93 and payment ME design. And one of the reasons we want to talk about this is we often get questions about what is the right value of resilient modulus to use. And there are some significant differences between resilient modulus as you use in AASHTO 93, which many agencies are still using and many agencies have experience with. So we want to distinguish the difference between those two resilient moduluses. I'll talk a little bit about default resilient modulus. So the number 2 part will be the bulk of the presentation. I'll talk about some default resilient modulus values that are included in payment ME design and what values to use. And then basically the presentation kind of talks about how to interpret resilient modulus, test results for proper application in payment ME design, and then selecting the proper resilient modulus inputs from lab testing and back calculation. So those are the different learning outcomes. And the outline is a little bit different from the learning outcomes, but by the time we go through this full outline, hopefully all of the different learning outcomes are achieved. So I'm going to start the presentation with describing a little bit about resilient modulus, how it is used in AASHTO 93, and then we'll pivot and see how to use resilient modulus in payment ME design, and then talk about the default resilient modulus that are in PMED software, and then talk a little bit about back calculating resilient modulus input for use in payment ME design. And I'll wrap it up once to kind of summarize all of these different items. I acknowledge and understand that most of our listeners' webinar participants have a lot of experience and expertise with resonant modulus, but we often have people who are a little bit less familiar with resonant modulus. So I'm going to start at this point in time to talk about what is resonant modulus. And the concept of resonant modulus started early in the 60s and 70s, and it came about when pavement researchers identified the importance of dynamic loading. Prior to the 60s, and especially the 50s and 40s, most of how you characterized pavement materials was based on static loading. And so the 60s and 70s was a time when people started thinking more about how exactly material behaves under dynamic loading versus static loading. And so resonant modulus is really a measure of the stiffness of material under repeated cyclic loads. And I'll talk about that in the next slide. And specifically, it is a very specific input, and it has to do with a specific test process. And I'll talk about some of that in a little bit. But the modulus itself is the ratio of the deviator stress to the recoverable or resilient strain. It's somewhat similar in concept to elastic modulus, but which is really a ratio of stress to strain when you're talking about a static loading condition. But we are now talking dynamic results, and so there's a little difference between a static result and a dynamic result. But the resilient modulus is really a dynamic result. Most static tests, like the CBR or the R value and so on, there are some static strength tests that are available, and you can correlate some of these dynamic resilient modulus values with those static values. And there are several correlations available to various degrees of confidence or statistical significance between those relationships. I'm not going to go into a lot of detail on that, but resilient modulus testing typically involves a load cell, like I showed in the previous image that you see on the right. There are different sets of apparatus that you can use for this, but this is one example of that. And you apply a load on, you confine, if you look at the top right here, you confine your specimen with a confining stress, and then you apply a deviator load. Typically, the deviator load is a pulse type load, and you load it for a certain duration, a tenth of a second, for example, and then you have a rest period. You could have the rest period, again, has changed over time, and different standards call for different rest periods, but you may typically see a 9/10 of a second of rest period following that. So if you repeat this and do this over time, your pavement, your material that you have, your sample or specimen that you're testing, will have a certain level of strain, and then you remove the load, and then some of that is recovered, and then you repeat it. You have a behavior that looks something like this on this chart. The resilient modulus then is just the recoverable part, and you see that in the case of this soil, there may be a plastic part that essentially gets accumulated over time. But the resilient modulus is this recoverable part, the ratio of this recoverable part to the stress that is applied or that is the deviator stress, that is this load stress that you're applying. So that's the definition of a resilient modulus. As you can see, it is pretty specific, and so it is measuring a specific property of that soil under some specific testing conditions. So we always have to keep in mind that there is a testing standard that then has to go with that, and the testing standard would determine some of the values that you might get. Why is it so important for us pavement engineers? As early as the 60s, researchers found, and then definitely a lot of work was done by a lot of pavement engineers in the 70s, that it was a key property for unbound material and a key input for pavement design. And the reason for that is that the dynamic aspect of the loading and and the way you can actually simulate field conditions, so you're adding a load and removing a load, kind of better approximate what might happen in the field. Obviously, there's no one way to actually model exactly what is happening in the field, but we want to characterize a material that, to the best of our ability, we can better be able to come close to how it might perform in the field. I pulled this quote from the AASHTO, the original AASHTO road test report, the HRB SR State Art 61E report from 1962. And one of the interesting things in this quote was the performance of flexible pavements was predicted with essentially the same precision from load deflection as from load design information. So if you, so very early on, engineers realized that the deflection of a pavement is a good measure of the performance of the pavement. And so that's why deflections and the measure of deflection become important when it comes to pavement design. As I mentioned before, resilient modulus is a specific input that is collected at a specific set of conditions. And so there have been standards, and I'm not going to go through the details on each of these different standards, but there have been standards that were developed. The first standard, the earliest AASHTO standard, was the T-307, which was in 1982. And then since there have been a few other standards, and the most common one that we see now is the AASHTO T-307, which first was published in 1999. But the main difference between many of these standards was that in the beginning, in the early 80s and in the 70s, the resilient modulus testing there were some challenges with reproducing results and with the consistency of getting the test values. So over time, a lot of research was done in this test, and it became better in terms of the specimen preparation, testing protocols, how to measure the deformations, where you measure it, the stress levels that you use. So there was some standardization and some quality control that was done to reduce the variability of the test. So what are some key factors that affect resilient modulus? I bolded the first two items because the first two items are material related items. So you may have a certain type of soil or aggregate, coarse aggregate, fine aggregates, whatever the soil is, that the type of material and how it behaves under a repeated load is a factor that affects resilient modulus. If you do something to that material, like adding stabilization agents like cement or lime, that affects the resilient modulus. But those are some intrinsic parameters that affect resilient modulus. But there are some extrinsic parameters that affect resilient modulus as well. And the extrinsic parameters include the stress. So resilient modulus is dependent on the stress level that the sample or soil feels at the time of the test or in the field conditions. So what is the stress that it is undergoing? And so it changes based on the applied deviator and confining pressures. Resilient modulus is highly sensitive to moisture and the density. And so those are properties that can change over time depending on how you prepare the specimen. So that impacts resilient modulus. And finally, environmental factors. So if you have seasonal variations, if you have frozen soil, freeze-thaw cycles, moisture changes, that is the previous bullet, all affect the resilient modulus, particularly of subgrade soil. Here are some examples of some resilient modulus. So, and some of this I will come back to, but just to give you some idea of how much the resilient modulus changes. On the left is a high plastic clay, and you can see under different levels of, so if you look at each one of these, there are three kind of related lines here. Each one of these is at a different deviator stress that is applied, and then as you go from one point to another, each one of these is at a different confining pressure that is applied. And as you go from one point to another, you're applying a different load stress to it. So you can see the confining pressure and the deviator stress impacts the resilient modulus. In this case, it can be as high as 9,000 and as low as 6,000 for this high plastic clay. And then for a low plastic clay, in this case, it can go from close to 10,000 to 5,000. So there's about 2 to 3 times a factor of difference in terms of resilient modulus in these two examples. For coarse grain soils and aggregate, you can see in this case, the coarse grain soil, again, somewhat similar to the last slide we saw. And there's a stress, you can see there's a stress dependent behavior here. That means depending on the stress, you're going to have a different resilient modulus value. And then to the right, you can see this aggregate base. If you can see, it can go from 10,000 up to 45,000, depending. And again, you may not be as high as 105 bulk stress, but let's say you go to the 65 range, you're still going from 10,000 to about 30,000 in terms of the resilient modulus of that aggregate base. So the take-home message is resilient modulus is really not one value. It's actually dependent on many different things. But if you think about how a pavement structure is, you have the structure of a pavement that the soil or subgrade or the subgrade soil or the base layer is sitting in, and you have a load that's applied. So the stresses are changing over because of that load. And so you are not having one value of resilient modulus technically. You're having many different potential values of the resilient modulus itself. So, so that gives you some background on resilient modulus and testing. Again, I didn't want to go into too much detail on that. There's a lot of people who have done a lot of good, important work in resilient modulus testing and how it impacts performance and so on. But let me come to what resilient modulus meant for AASHTO 93. Resilient modulus in AASHTO 93, if you recall AASHTO 93, the equation, the fundamental equation for AASHTO 93 really came from the AASHTO road test, which was in 1958 to 1960. And at the road test, which was done in Ottawa, Illinois, there was one soil type. That soil type had, let me come back to that. The original AASHTO equation really from the 1966 version of the AASHTO equation is just this number, 9.36 times log, blah, 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 until this log number. So this part was the original AASHTO equation. In 1986, with the 1986 guide, there was some, in the 72 guide, they added some regional factors, soil factor, but in the 72 guide. But the 1986 guide was the first time resilient modulus came about in the AASHTO road test, in the AASHTO guide. And that's this last two terms, the 2.32 times log resilient modulus minus 8.07. And then in the 93 guide, in the 86 guide, they also added this reliability portion. That's the first two terms. But let's look at the focus on this last term, the log resilient modulus times 2.32 and the 8.07. If you enter 3,000 as the resilient modulus here and take the log of that, you multiply that by 2.32, that's exactly 8.07. So these last two terms vanish when you use a resilient modulus of 3,000. And so the last two terms, really, the 3,000 was the resilient modulus of the AASHTO road test of the soils in Ottawa, Illinois at the AASHTO road test. So these terms come from some calibration done using soils that were not in the AASHTO road test, but from other data points that were used in order to add to the original AASHTO equation, the 9.36 and all of this, the log structural number and the log change in PSI and all of those terms. So this was done to essentially extrapolate the AASHTO road test to non-AASHTO soils. And the AASHTO, the 93 guide on the 86 guide also had kind of some correlational relationships between resilient modulus and the layer coefficients, which are the AI, which go into the structural number computation. And the 93 guide accounted for moisture separately. So what the 93 guide essentially said was the resilient modulus value that you're supposed to use in this equation is an in situ resilient modulus value. That means what is the expected resilient modulus value at this location through the life of the pavement. So there was a process also in the AASHTO guide to either to take some kind of weighted average based on the seasonal variations in resilient modulus and some damage computation. So you would have a seasonal way of adjusting the resilient modulus. But essentially, you also had this drainage coefficient that kind of you added to your different layers for your base and sub-base materials, but not for your subgrade, to account for the moisture in those layers. So to kind of put it together, the resilient modulus here is that of the subgrade, and there's a seasonal an adjustment that you could do weighted for the seasonality of the resilient modulus, and then resilient modulus of base is or the base characteristics are adjusted through the drainage coefficient for the moisture. So the AASHTO 93, again, I want to go back to this equation because we hear a lot about the resilient modulus of AASHTO 93, and I was not able to find a reference that kind of really showed where these calibration coefficients came from, the 2.32 and the 8.07. But one thing that I will say is that anytime you do calibrate, anytime you do have a model, you have to understand where that calibration coefficient came from. What were the values that were used for the calibration? So I don't know exactly. The guide itself does say use the optimum moisture content that it's experienced in the field, but I don't know where these 2.32 and 2.32 came from. And like I said, the 8.07 comes from the fact that the modulus is 3000 at the AASHTO road test. I want to talk a little bit about sensitivity and just this one slide, but if you use the AASHTO equation and for example, let's say you are off in the computation of the resilient modulus and you use a 10,000 resilient modulus versus a 15,000 resilient modulus. So between 10,000 and 15,000, it's about half a structural number. So I'd say that's equivalent to about one, maybe a little bit more than 1 inch of asphalt. And then between 10,000 and 20,000, it's about a structural number of maybe about 1 or so. So again, that's about 2 inches of asphalt. So if you're off by 2 or 3,000 in resilient modulus, you could be off by about half an inch of asphalt in your model for computing the structural number and then the thickness of asphalt that's required. So kind of keep that in mind because I'm going to talk about this when we look at the PMED sensitivity as well. So how is resilient modulus used in the AASHTO 93 guide? It's only used for flexible pavements. Starting the 86 guide, the AASHTO road test, resilient modulus was 3000 psi. AASHTO, and clearly at that time they used that model that was used in the 96 guide was the AASHTO T-307 test, and I'm presuming it's the average in situ estimated value is the 3000 psi. But there's the AASHTO guide also provided a lot of empirical correlations with static and strength tests. And I mentioned earlier, there is a procedure for seasonal adjustment for subgrade modulus, some empirical correlations with base, sub-base, layer coefficients, and then the drainage quality and climate of drainage coefficients are used for the unbound base and subbase to kind of account for moisture in those layers. And just, I think, one last slide on the 93 guide before we move on to Pavement MED design. The 93 guide had some of these quotes in the guide. Resilient modulus should normally be based on the properties of the compact layer. So they understood that compaction, in situ compaction was important. It's based on average resilient modulus values. And also it emphasized that you should not select a design resilient modulus value based on some minimum or conservative criteria. So use an average value. There is some mention of stress states in the AASHTO 93 guide, but not a whole lot. And so I don't think there was any kind of adjustment made, or there is any kind of adjustment made for stress states in the AASHTO 93 guide. In fact, I'm guessing you probably most agencies and most designers probably use the same resilient modulus values regardless of whether they're building a thin pavement or a thick pavement, whether the structure above the subgrade is substantial or not that substantial. But I think there was some understanding that stress states do impact the resilient modulus, but most agencies probably do not or did not adjust the resilient modulus depending on the stress state. I'm saying some of these right now because as we talk about PMED, you start understanding some of the differences when we and what we can do with Pavement MED design going forward. So the next probably about 15-20 minutes or so, I will talk about how resilient modulus is used in Pavement MED design. If you look at resilient modulus input in Pavement MED design, it allows you to select level 2 or level 3 in the Pavement MED design, and there is no option to select level 1 in the Pavement MED design for resilient modulus. You have two options. One is to modify, one is to let the software modify the resilient modulus based on the temperature and moisture in the pavement layers, and then also a user can enter some annual representative value that it can then just use as the resilient modulus for that. In level 2, you have essentially for level 2, the idea is you can use correlations of the material that you are going to have on the project, and those correlations. So you would do some lab test, whether it is on the soil for that project, and you could use correlations with CBR or R value, and use that, and the software has some correlational equations in there that you can then use as your resilient modulus. But this is the soil that you will encounter for that project, or the base or subbase that you might use in that project. At level 3, you would essentially just use some default value, a regional default value or a state default value, or maybe even the PMED provided default value for the resilient modulus. So that's how the software is currently set up. So this slide kind of somewhat summarizes that there is no level 1 right now in Pavement MED design, because the 137A, the MEPDG original models suggested that level 1 really should be a nonlinear stress-dependent resilient modulus parameters. That's K1, K2, K3. And it also requires the use of nonlinear finite element code, which is not currently in Pavement MED design. So ideally, if you really want to characterize unbound materials, you really need to do a nonlinear stress-dependent analysis of those materials and then model that appropriately using that. So the level 2 and level 3, where you specify the resident modulus directly or through empirical relationships with other index properties or use a default value. Has no stress dependence. It's essentially an individual value, and I have a question mark basically on no stress dependence because as we go forward, I'm going to talk about how you can kind of game the system, if you a little bit. I don't want to use the word game the system, but kind of use that, at least bring in some level of stress dependence into the model. An important thing to note is that for pavement MED design, the resilient modulus input is not your average in situ resilient modulus input that I mentioned with the AASHTO 93 guide. The resilient modulus input is the maximum dry density, is the resilient modulus at the maximum dry density and optimum moisture content. If you use representative values, of course, then that's then you're taking it upon yourself to say that these are the modulus values that the soil will encounter over the life of the pavement. But if you are going to enter resilient modulus values, it's not the in situ value; it's the maximum. It's the resilient modulus value at the maximum dry density and optimum moisture content. And I'll explain some of that in the next few slides. So essentially, if you go back to some of the soils engineering classes, when you take a soil and you compact it, at the optimum moisture content, you can have that's where you can achieve the maximum dry density for a given compactive effort. So these two curves that you see here are two different compactive efforts, but at a given compactive effort, you can achieve a certain density at that peak density at that optimum moisture content. The reason you enter the optimum moisture, the resilient modulus at the optimum moisture content and the maximum dry density is when you a pavement MED design, you enter in and I'm talking right now about new construction. So you have a base construction date right here, and then a pavement construction date and the traffic open date. So the base construction date, that's when it starts the moisture model and starts there's an assumption that the contractor does certain things in constructing the base, and then once that base is constructed, the moisture model that is built into Pavement MED starts moving moisture from the groundwater table and the soil water characteristic curve, moving the moisture through the pavement layers, and so the moisture model starts at that time. So, for example, if you have a 20-year design, the 20-year design is really from August 2009 here to, I guess, August 2029, but the moisture model actually starts June 2009 and then carries that on till August 2029. So the reason when the MEPDG was developed, the reason they did not use in situ values, but rather use the optimum moisture content and maximum dry density is there's a couple of important reasons. One is purposes of calibration, because majority of resilient modulus tests are typically performed on specimens at optimum conditions. So for database, for building databases and for calibration considerations, the resilient modulus on optimum conditions is used in MEPDG. The original MEPDG documents also say that the common practice is to require contracts to compact base to at least 95% of maximum dry density and subgrade to 95% of maximum dry density using the modified or standard Proctor. And the thinking was that a contractor will typically target above these minimum requirements. In order to achieve or in order to compact to these levels, they probably want to get the moisture at the optimum moisture content to basically get those densities. So the thinking was that good construction practices will force contractors to wet the material to near optimum to facilitate compaction. And so the thinking was that when the base is constructed, that it will be close to maximum dry density and optimum moisture content. So because of those two reasons, essentially that's the starting point, and also the data that we have for calibration is often at the optimum conditions. That's the reason MEPDG uses the optimum conditions for resident modulus. Keep in mind that the resident modulus, the software changes the modulus over time, and the moisture gets to an equilibrium moisture content that is calculated through the enhanced integrated climatic model, like I mentioned before, based on where the water table is, and then based on how the water moves through the soil. So let's look at the sensitivity of resident modulus in pavement ME design. And these are a couple of examples. Again, anytime I give this kind of examples, I always want to put the caveat in that this is one set of data for one specific set of conditions for one set of inputs, and cannot really be generalized to a full broad range of inputs. But a couple of examples here. The chart on the left shows a resident modulus from 8 to 22. And you can see the HMA thickness in this condition, maybe around 10, is about 7.5. And then if you go to about 20, it's about 6.5. So about 1 inch difference in HMA thickness. More likely than not, you may be off in your resident modulus only by maybe 2, 3, 4, 5,000 psi. And if that's the case, then your difference is really, let's say, from 12,000 to 16,000 is maybe about a quarter of an inch, maybe a little bit more in this case. So it kind of gives you, it's often useful to do a sensitivity analysis to see, do I really need that level of sensitivity in a certain parameter? And I'm not saying you do or don't, because it just depends on what the other inputs are. But it's always valuable to do a sensitivity and see how something impacts your layer thicknesses and your designs. If you look at the chart on the right, looking at this slightly differently, the green curve and the blue line here, you can see there's a low strength base with a 6-inch AC thickness, default strength base with a 6-inch AC thickness, and a high strength base with just 6-inch AC thickness. And you can see that the bottom of fatigue cracking from 0 to 20 years actually does change quite a bit based on the strength of the base. But if you increase that thickness from 6 inches to 8 inches, in this case, you can see that 2-inch thickness, inch difference in thickness kind of made up for that base. So you could use a low strength base, which is this guy, the green line, and add 2 inches of AC, you're now to this black line. But if you keep the same thickness of AC, that is 6 inches, you're from the green line to the blue line if you have a high strength base versus a low strength base. So a different way of looking at sensitivity in terms of the cracking, and this is in terms of the HMA thickness. So let me pivot a little bit from those inputs and talk a little bit more about the stress sensitivity of resilient modulus and how we can use that in pavement ME design. So there's a new standard that should be out soon. It has been balloted, and this is a standard practice for determination of the design resilient modulus for unbound layers for pavement design. So this is kind of gets us to a quasi level 1 resilient modulus. And when I say quasi level 1 resilient modulus, is that, as I mentioned before, a true level 1 really means you have to model the stress sensitivity. You might have to do a finite element modeling of the structure, but we can include a stress sensitivity in the resilient modulus value that we enter. So I mentioned resilient modulus is impacted by the test conditions, so the maximum bright density, the moisture content. But now we're saying, okay, let's also bring in the stress state that it encounters while the soil or the base, the material, the unbound material encounters while it is in situ conditions. So this procedure, this standard gives you a way for accounting for the stress state and using a resilient modulus value based on that stress state. I said quasi because it's only one stress sensitivity resilient modulus value is used. What you can do is you can enter this individual value as an input level 3. So the resilient modulus value that you would enter into the program, you could enter it at an input level 3, but it is a stress sensitive resilient modulus value. So it's a single value based on the stress state that might be typically encountered by a soil or a base by an unbound material in situ conditions. You might have to do an iterative procedure to match the stress rate, and I'll not necessarily with the structure, but with the resilient modulus, and I'll talk about that in one of the upcoming slides. But however, one thing I do want to mention, and I think I'll mention this one more time, but I put it here and I want to make sure I don't forget, is that whatever process you use, you want to be consistent between the values you use for calibration and the values you use for design. Cannot stress that enough. If you use stress sensitivity resilient modulus values for calibration, that's what you would use for design. If you don't use stress sensitive resilient modulus values for calibration, then you shouldn't use that for design. So you have to be consistent. And this is true about every domain that is within pavement ME design. The assumptions that are made in developing the calibration coefficients should be consistent with the assumptions that are made in doing the pavement design. So if you think about soil structure, you have your and I'm going to focus primarily on the asphalt pavements, but this discussion is somewhat true even for concrete pavements. But you have your asphalt layer, you have your base, and then you have your subgrade, and you can see that because of all these layers, you have these unbound materials at a different stress state than if they were just loose materials. And so we have to account for this and the stress state that it is under. If here's one example, and this is an example from the standard itself, but if you do the resilient modulus testing and you have the resilient modulus testing allows you to have a confining pressure. And so if you have a confining pressure, in this case of 6 psi, 4 psi, and 2 psi, and then you add the deviator load, that is the load that you apply and release in a cyclic manner of 2, 4, 6, 8, and 10 psi at each of these three levels, you can combine those numbers, combine the total stress to get a bulk stress, which is essentially in this case 3 times the confining pressure plus the the deviator stress. So 3 times 6 plus 2 is 20. And then that'll give you a bulk stress. So you have at different bulk stress values, you have a resident modulus value. So one thing to note here is that you can see that the modulus values can change depending on the confining pressure for this particular soil. As the deviator stress increases, the modulus values decrease. And then here you have the confining pressure going from 6 to 4 to 2. And you can see that the higher the confining pressure in this case, you have higher resident modulus. So this is typical behavior of a silty, clayey type soil. When you confine it, it actually oftentimes have higher modulus values. So in Pavement ME design, in order to so in this standard that I mentioned, in this standard practice that I mentioned, what you want to do is start with the laboratory testing, and you have your laboratory testing. You test the material at different confining pressures and at different deviator stresses, and then you develop a kind of use this data that we have to develop a constitute model. So there's the standard has a couple of different, 2 or 3 different examples of this. In this case, and I'm not going to go through each one of those, but in this case, the resident modulus is related to the stresses through this equation. This is the bulk stress theta, and you have the stresses in the other directions, and that gives you the shear stress, the octahedral shear stress, and you use that data to obtain these coefficients K1, K2, K3. So that gives you a constitutive model for this soil based on the data I just showed you in the last slide. Now, in cases of some soils, you could have a simpler equation. For example, if you have a granular soil, you could just have the K1 and then theta to the power K2, and that will give you a model as well. So there's a few different functional forms that you could use. So you start by developing that, and the reason you do that will become a little bit more clear when we come to the point of picking the right resident modulus values, because we could potentially probably just eyeball it from these numbers, but we're engineers, so we don't want to just eyeball numbers. So you come up with these equations based on the data you have. So Harold von Quintus and some of his colleagues have done this work for decades. And in the late 1990s, I think it was 97, 98, they published some work on back calculation and resident modulus. And so how to combine how to use back calculation modulus values, and how do they relate to the laboratory resident modulus values. So based on that, in those reports, they came up with a location where to calculate your stresses, and the location, the strains and the responses, and the location that they came up with is that in a base and sub-base, you go to quarter the depth of the layers, and then in the subgrade, you go 16 inches into the subgrade. I have option A here, and you'll see this in this slide, in some of the coming slides, because there's another slightly different way that we could go about this, but I'm going to start with this option. So you take these points in this, and so this is a kind of a busy chart. I'm going to try to explain it the best I can. But what we are trying to do is we are simulating. So if you think about let's just focus on the subgrade for now, and then what we talk about the base is kind of similar. But if you take a point in the subgrade, in the lab, you have the stresses that is basically your confining stress, which would be the same in all directions. And then you add your deviator stress to that, which is the load that you add to that. So you may have a point in the sample, and you have the stresses, and then you have a deviator load that is applied. In the field, it's a little bit different. In the field, you now have the overburden, that is essentially the weight of the material that's above it. And then, so that's the stress that's in that direction. And then you have the stresses in the horizontal direction. Keep in mind, this point is in equilibrium. So you have the stresses in the horizontal direction. That is basically what is confining or holding this point in space and keeping it from moving. And that confinement is related to this overburden. And so you have and let's talk about this without bringing in the wheel load at this point in time. And so you have that point in space, and so it's being confined in this direction. And there's usually a relationship between this overburden and this confinement. So you have the confinement and the overburden, and now you bring in the load. When you bring in the load, you now have an additional stress that's created on this in the vertical direction, and then you have some change that is also happening in the horizontal direction. So, so to put it all together, and in this case, and in most cases, there's really no difference between your X and Y, but there is a difference between your X and Z or your Y and Z. So you have this point in space. So so let's start by what we need to do. So we start by first not having the load and just looking at what is the overburden, and that is essentially just the weight. So you take the thickness of each of the layers, multiply that by the density, and add all of that. So if any given point in space, so here, for example, if you have a 6-inch HMA, you take the 6-inch, multiply that by density. If you have a 6-inch base, you take the 6-inch of the base, multiply that by the density of the base, and then you have or the unit weight, and then you have the soil that's above this point, which I said we should use 18 inches for the subgrade. You take that 18 inches and then multiply that by the unit weight of that soil. So that gives you essentially the stress on top of that. And the stress, and right now I'm not talking about the load, we're just talking about this material that's above it. And the stress that's in the horizontal direction is related to that by a K factor. And this K can be anywhere from 0.5 to more than 1, actually. And so depending on, and the standard that I mentioned has some guidance on the numbers to use. Typically, you might see 0.85 for a clay or silty soil. You might see 0.65 for the granular base in that standard. If you have overload conditions, you might even have greater than 1. So it just depends on there's some guidance in that document for this K value. So you start by essentially taking those stresses in the horizontal and vertical direction. That's your at-rest stress. Then you add the load-related stress. Now, the only way to get the load-related, so that at-rest stress is easily calculatable. We can easily calculate that. You add the load-related stress. The load-related stress comes from elastic layer programs such as WinJulia. So now you add the load, and then you see what the stresses are due to the application of the load. And so you now have those numbers. You get the bulk stress from this from the at-rest, and then you add the load-related bulk stress. And so when you add those numbers, you get a bulk stress, and then you have that number. You may need to iterate one or more time. If there's 2 ways you can do this. You may need to iterate, like I said earlier, 1 or more times, because in order to get WinJulia going, you have to enter a modulus value in there. So you may guess a modulus value for WinJulia for this layer. Let's say you guess 15,000. You do this one time, and then you say that my computation actually says 20,000, you put in 20,000 back in the program and then do it again. And maybe within 1 or 2 iterations, you should be able to kind of zoom in on the modulus value. So the guidance is to start with the lowest layer, that's your subgrade, and then do your base layers. Okay, so what do we want to do? So here's an example of this in kind of, and there's a few examples in that standard. So once we're done, you should probably, if you have a chance, once the standard becomes official, review that standard. But here's an example. In this example, you have a soil, that's a sandy soil. You have under the 2, 4, and 6 confinement, these are the curves. But if you develop the constitutive model, then at just this 2.71 psi, then that becomes this dashed line. And then you do your Wien-Julia computation, and the Wien-Julia computation gives you a bulk stress of 10,000 in this case, or 10 psi. And so where that point intersects, that would be the resilient modulus value that you would need to use for design. In this case, it's the 16,000 psi of the resilient modulus value. So you can see that this soil, the resilient modulus goes from 8,000 to 18,000, but under the conditions that these computations were made, and this is one specific example with one specific structure and one specific soil, 16,000 would be the proper resilient modulus to use. Obviously, that's going to depend on the load you use, and there's some guidance on the load you would use. And in the standard, I think it's okay to use a single axle, typical 18 kip single axle or 20,000 or something like that. It's not very sensitive to that. The confining pressure is really what dictates the modulus for the most part. Here's another example. This is a crushed stone base, and you can see here that there's a difference between this curve and the constitutive model at the 2.71 psi. So in this case, you have a different type of constitutive model, which actually depends on the confining pressure. In the case of this crushed stone base, you can have a more like a single model that combines all of them. So in this case, the lab modulus change goes from maybe about 16,000, 18,000 to about 35,000 psi for this base. The dashed line is the fitted line. And what you could do is, instead of doing an iteration with the resilient modulus in Wien-Julia, you can actually do multiple computations at different resilient modulus and plot a curve. And you plot the curve, and then where it intersects, that would be the point. In this case, this equation is just bulk stress, because there's a difference between the constitutive model form for this one versus this one. So in this case, it's just the bulk stress model. So this is the point where it intersects, and then that would be the resilient modulus value that you would use. So about 23,000 psi, as opposed to 38,000, or even 16,000. So that would be the resilient modulus value to use for that layer. So this kind of summarizes, or this kind of gives you some idea of the impact. And again, one example, one set of conditions, one scenario. There's the top is a coarse grain soil, and then a fine grain soil. And the different types of base, you can see when you have a thin structure, 2-inch structure versus 12-inch structure, the subgrade soil, very small difference in the resilient modulus that is selected, both for fine grain and for coarse grain. But for the aggregate base, you can see the thin structure, 2-inch versus 12-inch structure can make a difference in the resonant modulus values you use for the aggregate base. And here's another example. This is from the LTPP lab, LTPP sections for some LTPP sections for different soils. The MEPDG default value is shown here, and then the lab results for thin pavement versus thick pavement. So that it can be different than the default value. So I'm going to talk about default values in a little bit, but the values that you would need to use can be different from the default resilient modulus values. So I'm going to have a couple of slides on option B, and option B is less detailed than option A that I just showed. You could just say, you know what, I'm not going to do this. I don't want to run WinJulia, and I don't want to do this, that, or the other. You can just go to these tables. You can just say that, if my structure is between these ranges, 12 to 24, 24 to 32, greater than 32, I'm going to use the confining pressure that's shown here, and then the bulk stress that's shown here for depending on whether I have a rigid pavement or a thin flexible or less than 9-inch flexible pavement or greater than 9-inch flexible pavement. So you can then just take these points, go to your charts or your constitutive equations, and then just use the resilient modulus values that you get from these tables. So this is for your subgrade, and then for your aggregate base, something similar. You can just go to your constitutive equation or your resilient modulus test directly, and then just look at this table and pick up the bulk stress, and then look at what is the resilient modulus at that bulk stress. So if you choose option B, then it's you don't have to do the stress computations using the response computations using WinJulia. So let me talk a little bit. I think I have 1 or 2 slides on default resilient modulus values, and the default resilient modulus values, there's a small error in the manual of practice that I wanted to point out. But I'm going to start in the rightmost column in this table. So you have your soil types, A1A through A76, and in the original MEPDG, that was the in the late 90s, early 2000s when it came out. You have 40,000, 38,000, 29,000, 32,000, and so on for the resilient modulus values. Harold, Witzak, and others did some work under 140D where they looked at resilient modulus values, and I think Claudia Zapata was also part of that team. They looked at resilient modulus values for LTPP sections, and they found that resilient modulus values were 29,650. These are the mean resilient modulus values for different soils that were in the database that belonged to that class. These are adjusted. These are adjusted. The database actually has, I think, in situ conditions, but they were adjusted for maximum dry density, optimum moisture content. So once those adjustments were made, you have, and also those were back calculators. So the adjustments were made for the back calculation part, which I'll get to in a little bit. But once those adjustments were made, these were the values that they came up with, which is this 140D column. And then based on that, they recommended essentially 29,500, 26,500, 24,500, 21,500, 21,000, 20,000, 16,500, and so on for the recommended values from the 140D. And that's what you see in the manual of practice. So if you look at the manual of practice, you'll see 29.5, 26.5. That came from the 140D. However, I did want to point out there's actually an error in the manual of practice, and that error came from, I think, a copy and paste. So if you look at the manual of practice, and I have that here on the right, you can see the sequence is A1A, A1B, A24, A25, A26, A27, A3. But the 140D has A1A, A1B, A3, A24, A25, A26, A27. And because of that copy and paste error, some of these got shifted by a little bit. And so these 5 numbers are shifted. So if you look at, for example, the manual of practice says 16,500, 16,500, A3, that's what it says here, 16,500, but the 140D actually recommended 24,500 because the mean number in the LTPP database was 24,697. So this is an error. So if you actually you can see they're transposed by 1. So you can see the 24,500 is this number, the 21,500 is this number, the 21,000 is this number, the 20,500 is this number, and then the 16,500 is this number. So because of that copy and paste error, there's compared to the 140D, the MOP numbers are off from the 140D recommended values. That's for flexible, and then the MOP also has numbers for rigid, and there's assumption of stress sensitivity under a rigid pavement that makes this modulus different from the flexible. The PMED software default inputs are basically the rigid default inputs. And what I say about defaults is it's a good starting point, but really it's best to have local defaults and what you have with your own database rather than what's in the software. The software defaults are primarily there to be able to run the software and give some starting point for getting some results, where you really should be using values that are known to you for that particular material. Okay, so the MOP has these numbers off by a little bit. So if you want to correct the MOP, you would actually just say that the A3 is the 24,500, and then the A24 is 21,500, A25 is 21,000, A26 is 2,500, A27 is 16,500. So that would be the correction to be made. So I'm going to wrap this presentation up in the next 5 minutes and talk about back calculation. When you do back calculation, it's what you're really computing is not a residual modulus, and it's not an elastic modulus. You're computing something, as I mentioned, elastic modulus is really a static measure, and resilient modulus is really a specific lab measure based on specific lab conditions. When you drop a load, you're kind of in a dynamic situation because you're dropping a load and the pavement responses are at the surface of the pavement. As you can see in this schematic, the deflections at the surface of pavement is a response to that dynamic load that you just dropped. And because it is a response on the surface to a drop dynamic load, animation there for you. A drop dynamic load, it really is not a elastic modulus per se, but it's not a resilient modulus either, because by the time, because you're really not measuring right under that load, you're interpolating or technically back calculating based on these deflections, and there's a lag time and time it takes for these sensors to get the responses based on the drop load. There are other factors why this drop load and then the back calculation procedure results does not directly match a resilient modulus value. And so when you use a back calculated modulus value, it's technically not a resonant modulus. It is a back calculated modulus. And so you have to tie that in to a resonant modulus. And in order to tie that into a resonant modulus, you multiply it by a C factor. And this C factor is an example here for different conditions, different locations, depending on PCC or AC or embankment, and then the aggregate base and subbase versus subgrade. So you have this correction factor. So you back calculate a modulus, and then you multiply it by this correction factor, and that is the value that you use as a resonant modulus value in Pavement ME design. Note that at this point in time, we are less concerned about the maximum dry density and optimum moisture content because we're now in a back calculation. We're now in a rehabilitation scenario, and the pavement. So what you're back calculating is already an in situ value, and the model will start at this point when you run the Pavement ME design. So with a couple more slides and then I'll wrap this up. But if you choose rehabilitation level 1 in pavement design, so when you go to the AC properties and you choose, when you go to the layer properties and you go to the rehabilitation tab, you choose the rehabilitation level 1. When you do that, then within your layer properties, and specifically if you select the unbound layers, in this case the subgrade, I believe I chose, the subgrade, you can see the C factor, and then you enter in the C factor to multiply the resonant modulus to adjust the resonant modulus value, that back calculated resonant modulus value to a lab resonant modulus value. So we covered a lot of things in today's presentation, and the key thing that I want to kind of summarize some thoughts is resonant modulus is an important input, and it's necessary to characterize unbound materials. You can be, depending on the values you choose, it can make a difference quite a bit on the distresses modeled, but at the very least, an inch or two of asphalt if your thickness, and maybe half an inch, depending on how off you are, the resonant modulus can impact your design thicknesses. There is differences in use between AASHTO 93 and Pavement ME design. Like I mentioned, the key difference being AASHTO 93 really is an in situ modulus, and Pavement ME design is a maximum dry density, optimum moisture content modulus value. But there's other differences also. AASHTO 93 was a different test standard than the PMED standard, the T-307 versus the T-274. We talked about how you can adjust the resonant modulus to account for stress state, but as I mentioned before, I will say this over and over again, is you want to be consistent. Make sure you have the same modulus values you use for calibration, the same procedures for your modulus values you use for calibration that you use for design. And then when it comes to back calculation, you have to adjust to the in situ lab resonant modulus values through the C factor. So that is the end of the presentation. I'm going to do a couple of polls, and then we can answer any questions that have not been answered yet. Okay. So let's get to some questions. There's I appreciate my colleagues, Harold and I believe John and others answered some of the questions online, and there seems like a lot of questions. So I'm glad 27 questions were answered, and there's 8 more questions open. So I'm going to address that to the best of my ability. So, or 7 more questions open. Jay says
you can see the questions, correct, Sri?
Yeah, I can see the questions.
Okay.
Yeah.
Okay.
Yeah, thank you. and I think some of them are being answered even as I speak. So one question just vanished. Actually, two just vanished. So there are only 6 open questions now. So if I stay long enough, I think Harold will answer all these questions, and I don't have to worry about it. Uh, let's see. Jay says we may not get to it, but how does the biaxial geograde affect the resilient modulus of the subgrade? And see, HRP 235 modifies the aggregate base course and subgrade modulus based on where the grid is placed in the ABC layer. Should we use the enhanced modulus throughout the subgrade layer, or should we limit the enhanced modulus to the top 6 inches or so of the subgrade when we place the grid at the bottom of the ABC layer? To answer Jay's question, I don't have a scientific basis for answering your question. I don't think, I'm sure some of the GeoGrid folks have done research on this. From a modeling perspective, we are behind in terms of our ability to model geogrids. So whether the impact of a geogrid is only in the top 6 inches, or you can account for it, the bump in modulus to the entire structure, I don't know if it makes that much of a difference, to be honest. We'll have to run the numbers and see. I think I would probably limit it to the top 12 inches or 18 inches or so, but I don't have a scientific basis for saying that. Again, it may be worth doing some analysis, some exercises, and see, is it even sensitive? Can I, if I just do the top 6 inches or top 12 inches or top 18 inches or entire subgrade, does it add any significant change, anything significant to my results? My guess is in most cases is probably not. Now, if you have a poor soil, it is possible that it has more of an impact, but without doing a sensitivity and without the knowledge, I can't say for sure what is the right number here. I know a lot of agencies limit it to the top 6 to 12 inches, but I don't know if there's a strong scientific basis for that. I think all the questions are answered. So appreciate it, Harold and John. And let me see. Hari, I think that's it with the questions. And I believe,
Harold, do you want to say something? I saw your hands.
Oh, Harold, go ahead.
What I was just going to note is we've answered, John and I think have answered most of the questions that were asked. If we didn't explain something properly in typing out an answer, I guess to the group, please feel free to type in another question, or to basically send your question to one of us externally. I think Sheree, these will be the questions and answered. They're usually published along with the webinar on the Pavement ME site, correct?
I believe, I don't know about the Q&A, but Ben can clarify that.
We are good with Q&A, and we can always look at the questions afterwards.
Yeah, and to echo Harold's point, if there's something in the webinar that I didn't explain properly, certainly if I created more confusion than answers, certainly send us an email and we'll respond to that.
Shri, you have a few more slides to go, right?
Yes, correct.
Okay.
So let me go to those slides and then we can wrap this up. So again, I appreciate everybody attending the webinar. Here's the contact information on the Pavement ME design. On AASHTO side, it's Ben, who's Ben Said, and then Hari Nar. And then this is the website for ME design, the help desk, Pavement ME design at ARA.com, or call the 217-356-4500 number and reach out to us if you ask any specific questions. And then also seeing the Pavement ME team and all of our email addresses, including myself, Chad Becker for software, John Wooder, Abu, and Harold for engineering related questions. And I don't know, Ben, do you usually talk about this, or should I say something?
I got it.
Okay.
So there was a couple of first of all, thank you, Shri. Excellent presentation, and thanks to everyone for taking your time and joining us here. I just wanted to mention a couple of additional resources out there. If you liked what you saw today, there's some really good training content. All of the previous webinars are all on our YouTube channel, so you can find all of those recordings to share with colleagues. And in addition, this webinar, I think we got a couple of questions in the Q&A box about this. This webinar will be distributed shortly after we end. You'll get an email with a link, and it will be to this YouTube channel as well. In addition to software-specific trainings, there is a training course on the transportation.org AASHTO store that goes into depth on the manual of practice, MEPDG, and the principles behind it, and not just the PMED software. So if that's of interest to you or your agency or colleagues, head over to store.transportation.org /trainings for more information there. Shri, back to you.
All right. Well, thank you again very much, everybody. Thank you for your time and for participating and for the Q&A. And like I said, feel free to reach out to us and have a good rest of the afternoon.